Yeah, so.
Mm-hmm.
All right, welcome everybody to today's GS seminar. Today we are delighted to have Professor Qian Wang from University of Oxford. Professor Wang primarily works on differential equations and application to mathematical relativity and other topics. And she has done so many works. I'll just mention, some of her notable works. So one of my favorite is, the improved breakdown criteria for Einstein vacuum equations. And she also did a lot of work on rough solutions of the Einstein equations, causal geometry of rough solution of Einstein equations. She developed a new method for studying wave equations, such as geometric aspect for the method of descent, and so on and so forth. And also one of her major work is the rough solution of the other equations, which we are going to hear today. So without further delay, Professor Wang, please take away.
Okay, thank you. Thank you for the thorough introduction. And also thank you for the invitation. So today the topic is not quite usual for a GR group, but well, you can see it's closer to GR than the fluid. So it's rough solution for 3D, 3 space dimension compressible Euler equations. Let me go for setting up the equation. So we consider the compressible Euler equations of 3 dimension for a perfect fluid under barotropic equation of state. So pressure is assumed to be a function of density. Here, this density is positive valued in a positive valued function in space-time, written as P rho. And we usually, in this talk, we will go for this normalized density, which is defined by taking rho logarithmic of rho over rho bar. So this rho bar is certain constant background density. And also the sound speed is computed by just taking square root of dp by d rho. So with C and also V, we are going to define acoustic metric. And here, this V is the velocity of the compressible fluid. So it's 3 vector field in space-time. And with them, we can write down the acoustic metric, which is in 3. And so we're going to talk about some, basically, it's local well-posedness results. So we're going to focus on space-time slab with time, like lifespan is up to t, and t is a certain small number between 0 and 1. So if you compute the inverse metric, it is taken this way. And here, this capital T bold font is the future directed time-like uninormal of the level set of T. And it's decomposed in this way here. This VA partial A is running from 1 to 3. I'm using Einstein convention for denoting it. And and also restricted on the level set of T, the induced metric GIJ is conformally flat. So it's C to the negative 2 of standard Euclidean metric delta ij. So this is roughly the kind of the setup for the acoustical metric. And let me then, using this, sometimes you call it material derivative. For me, it's just T, time like future directed uninormal. So with T, I can write down the compressible Euler equation, and it's in 4. So it's a set of transport equation. One is for T rho, and one set is for TV. And this dV is the standard divergence in Euclidean space. And also we denote by W here, which is the vorticity, is the you use this standard volume form to contract with this gradient V. And so also we sometimes normalize it for convenience, use omega instead of W itself, and just by multiplying a factor e to the negative rho. So since W is a curve, so D div curve is 0, so div w is 0, and because I mean sometimes it's also we work with omega instead of w, therefore you can see div omega is certain nice equation. The right hand side has one derivative lower, and also t omega is also a nice equation. The right hand side also has kind of is a lower order term, and so I'm going to instead of working on this transport equation on rho and v, I'm going to bring it into kind of more like wave or GR type of treatment. So go to the next page. I'm going to just write this Euler equation in the form of box G v box G rho. I'm going to just compute the wave equation for them. And so it turns out to be something which looks complicated, but it's not that bad. So this box G is the standard Laplace-Beltrami operator of the Lorentzian metric G, acoustic metric, and also the right-hand side, I put a curve omega with the curve with this e to the rho c square in the red box. This is the main difference to me in comparison with what I'm more familiar with. And qi and q naught here are both quadratic terms in terms of d rho or dv. So here c prime is c is a function of rho. C prime is just its first derivative of c rho. So this is general the structure of the wave equation for v and rho. And if you're curious about derivation, you can check the paper by Jonathan Luke and Gerald Speck. They have the full derivation for it. So in the case that curve omega is 0, the system is then it can be reduced to cosine linear wave equation. I'm going to move to the next page talking about cosine linear wave equation. So before moving to the next page, is there any questions so far? If there's no, I move to the next page. So yeah, as I said, I mentioned cosine linear wave equation, and for convenience, I write this equation as the standard type, which is kind of slightly more simplified than the previous ones. So if you look at the wave operator on the left-hand side of the equation, the highest order term, partial I, partial j, the coefficient in front of it still depend on the solution. So this shows it's a cosine linear equation. And hij here is assumed to be uniformly elliptic. And if you look at the quadratic term on the right-hand side, here n alpha beta is a smooth function and about its variable, but phi itself, including for hij phi itself would be, in our setup, would be rough. So the problem will be like if you're working with some equation in kind of rough background, hij rough background is this Lorentzian metric. And then what can you get? So so this is just a slightly simplified model, but it already includes kind of heuristically this two type of important cosine linear wave equations. One is the irrotational fluid, which is what I said when this red box vanishes. And the other one is the Einstein vacuum equation under the wave coordinates. So it essentially is essentially the same, includes all this kind of essential difficulty. And so there has been a long history for studying the local well-posedness of this type of equation for data in certain HS space. And there will be a list of like literatures on it. So it started from Schopenhauer, and where this S is maybe way bigger than 4, but anyway, so that's the first work on this. And if you use the standard Sobolev embedding, energy estimate and iteration argument, you can reach S greater than phi half. So up to this point, I call them all classical solution. For any s below than less than equal to 5/2, I will call them all rough solutions. So move to the next page. These are the history for cosine linear wave equations. Sorry. So for the method for kind of establishing the local wave poses for rough solutions, actually are based on establishing Strichartz estimate, and the whole bunch of thing. Actually, I mean, the Strichartz estimate itself, I mean, in the rough background, started from the work of Smith. So he actually didn't think about cosine linear wave equation. What he thought the work was on linear wave equation with rough coefficient. The goal was to achieve sharp Strichartz estimate. For that purpose, he actually made assumptions about coefficient, and the work itself is quite sharp, but it's not tailored to do the results. So based on if you just change the strategy a little bit, just be a bit more strategic. If you are not aiming at doing sharp Strichartz estimate, just do something, because Strichartz estimate is with a bit loss can save you derivative anyway. Based on that kind of relaxed strategy, you can close the arguments at certain loss, but still gain over 5/2. So for instance, if you look at these tiny numbers, this is you allow certain 1/4 loss for Strichartz estimate, 1/6 loss for Strichartz estimate. With a bit of loss for Strichartz estimate, you actually can achieve better results, in particular for cosine linear wave equation. So it started up from Bohara-Shannon, and then by Tataru, and then Tataru made improvement over himself, and then Kleiniman introduced a new method, which is commuting vector field approach to do Strichartz estimate. So then he reproduced Tataru's work, and also introduced the geometric an important geometric structure, so that then they can carry on to improve the results to this number. So again, the number itself, although lower and lower, but it's actually, I mean, what's more important is the method itself is better and better. So so this is a long time ago anyway. So they achieve, by using commuting vector field approach, they achieve this result for s greater than this number. But the method of vector field method is actually more geometric. So for Einstein vacuum equation in particular, this is a very geometric equation. So they can achieve s greater than 2. This is Einstein vacuum equation under wave coordinate gauge. So this result itself is actually a sharp result. There is a counter example offered by Littlewood-Paley saying you can achieve Laplace for s equal to 2 for EV under wave coordinate gauge. And but for general cosine linear wave equation is actually harder than Einstein vacuum, and its s greater than 2 result is actually established by Smith-Tataru, and not by commuting vector field, is by constructing parametrics and using grid packet, something more Fourier. So it's actually already a sharp result for general cosine linear wave equation, and also there's counterexample offered by Littlewood again, and so saying this is a sharp result. Even for semi-linear case, you wouldn't expect better results. So it seems to be the end of the story for this the whole thing. And at that time, so I started to look at the whole material at 2010 something. Yeah, so at that time, I think, okay, so my initiative, it was to just reproduce this result by using commuting vector field approach. So that was at this level. So I was wondering why they couldn't push further. So it took me a while to understand it. And so at the beginning, I feel there are some technical redundancy in the whole framework. So the initial start the initial step is to kind of remove that. And but at the time I could only do it for Einstein vacuum equation with certain gauge. So I choose a different gauge. This is CMC spatial harmonic gauge. And so later I realized that maybe Einstein vacuum equation is too good. It may not be that helpful for me to kind of push, just make the ones in this general cosine linear wave equation. So it took me another 2 years for kind of really reaching to this, to complete this by using the commuting vector field approach. So, so for this is the story for general cosine linear wave equation. S greater than 2 is already sharp, and it also includes the irrotational fluid. So, but for Einstein vacuum equation itself, you can expect better results. So, if not choosing wave coordinate gauge, I need to mention this work, the resolution of L2 curvature conjecture. This is for Einstein vacuum equation with maximal foliation gauge. So they actually, it relies on a different type, because this equation at this under this gauge takes kind of verifies null form condition. So due to this special structure, you expect to be like to establish slightly better, you can have bilinear estimates. Of course, that's quite difficult because it's for cosine linear. So they, for the first time, establish bilinear estimate for the cosine linear wave equation, and then achieve S equals to 2 for Einstein under this gauge. So this is a very long work. But again, this opens the door for if you hope something lower, because the scaling for the scaling situation, scaling number for Einstein equation or just cosine linear wave equation is in 3D is 3/2. But of course, it's still quite out of reach to reach that level. And also for general cosine linear wave equation, it's hopeless because the structure is too general. But you can always dream it could happen for some nice equation. Probably, I'm not quite sure if Einstein is nice enough, but anyway, you can have a hope on this. So these are all something kind of related to GR. Now, so I will move on to the next page and talking about compressible Euler. So is there any questions so far?
Can you go up to like, S equals 2 in CMC SH gauge? Like,
sorry, S equals to 2 in CMC.
CMC SH, yeah.
CMC SH, I don't quite know if it satisfied. So they use, so the maximal foliation gauge they use actually is shift in this. There's no shift. So
right.
Yeah, so I can't tell because yeah, you need to look at the equation itself. So it's still very strictly depending on the right hand side if it has null form condition. Right. It's shift, but it's possible. It's still possible because shift itself is not a very hard thing. Yeah. It's like elliptic. You can control it. Exactly. But it may break the structure in some sense. Right. You never know. So at the S equals 2 level, probably there's a hope. But if there's some subtlety, in particular in Maxwell Color Gordon. I remember S is equal to 3/2, sort of is unreachable, but because of of course, So anyway, so there's some subtlety if you aim further lower. Anyway, that's a good question. So now I'm going to look at the general general compressible Euler equation. So what do we know about it? So initially we don't know much. We know this classic result at the level of 0 in HSS greater than 5/2. This is due to Kato and Maeda, etc. And also irrotational case is covered already, as I said, by Tataru and also Smith-Tataru and also my result. And for S greater than 2. And if it's incompressible Euler equation and everything's is kind of reduced to just depending on vorticity itself. So again, it's at the level of Sobolev level. So it's S prime greater than 3/2 is identical to like V rho at that level is greater than 5/2. So, in the incompressible case, S prime greater than 3/2 is already sharp due to the result of Bergan-Li. So one of my friend, after seeing the work of Bergan-Li, asked me to think about what would be the optimal result for the compressible Euler equations. So at that time, I think it's like 2016 something. At that time, I started to look at this compressible Euler equation, and I tried to answer this question. So well, the statement is a bit misleading. So I said separate analysis of two extremal cases lead me to propose the following conjecture. Actually, there is some calculation behind it. It's not really just cooking up the result by combining two. So the conjecture I have spent a long while to on is the following. So the solution of velocity, density, and vorticity of the compressible Euler equation in 3D is well posed for a short period of time with some t greater than 0 if the data satisfy initially this boundedness assumption, that is V normalized density are both bounded, and sound speed has a strictly positive lower bound. So this is my boundedness assumption, and also if the initial data dv, d rho, and w are in hs minus 1, hs minus 1, and hs prime, here s is greater than 2, s prime is greater than 3/2. So, and this just, if you think about the two extremal cases, these are kind of exactly matching those two cases. And here, this partial is space derivative. So this is the sort of what I aimed at. And a remark about this is if I further assume the pressure function is satisfy gamma law, so that means P rho, it can be written as some constant multiple of rho to the gamma, and this gamma is certain positive constant. And then the second assumption in 9 can be derived by using the first assumption. So you can remove one. Also connected to this, so if, I mean, so far I didn't assume anything for P rho, but if you, I mean, I wouldn't mind if, well, for achieving this, for solving the conjecture, I wouldn't mind to assume more. For instance, assume the pressure law for P rho. So if that helps, I would assume it without hesitation. But so far I didn't see if that's really crucially helpful. So this is something that I kind of have been worked on for a long while. But so today I can still only give you this version. So this is so far I could have a close complete story for. So this in comparison to the previous one, I still have to add a half derivative to this one. So let me give you the statement. So sorry. So let's S and S prime be fixed, and S prime is in between 2 and S, so smaller than S. And for the given data set, V rho W satisfying the boundedness assumption, and also any bound, no need to be small, such that if the initial energy for V rho and W in this HS, and HS prime space is bounded by M, and then we can have T star, which is a positive lifespan, and a new bound M1, depending merely on C1, C0 in 9, and S prime in our theorem 1, and the bound M, and a unique set of solution for the Euler compressible Euler equation. And they still satisfy, they still stay in the same energy space as they started from, and also satisfying this kind of bounds on this dv d rho, this both from d partial is representing both time derivative and also space derivative. So you have control on partial v, partial rho in this norm, and also there's the energy bound and also the bound for v rho have a new bound m1, depending on those constants, and and also in the lifespan. So there is a technical assumption about upper bound of S prime for this energy estimate, but this is not important anyway. So this is the main statement. There is a kind of ugly number here. I can't draw it. So as this one. Anyway, so so far, is there any question about the main theorem? If there is no, I will move to the remarks. So the remarks will be just on formality. So for instance, I assume things about partial v. So actually you can replace the assumption on partial v by dv, because you can always apply elliptic estimate for this hard operator div and cur in R3. So since you already assume something on W, so that's already cur v. So anyway, so this is kind of just the formality. We can recover the estimate, the bound on partial v, as long as we if we just assume dv and cur v. So the second thing is about the again formality. So the boundedness and assumption on 9 is sort of L infinity. If you don't like it, you can replace it by some L2 norm of v minus v bar, rho minus rho bar. Here rho bar, v bar are some constant states, and so then you can use other assumptions together with this boundedness L2 norms. Then just by using Sobolev embedding, you can recover the boundedness assumption for v rho in 9. So that's also just formality. And then d rho can be exchangeable to tv, and w can be exchangeable to omega. And also, again, the S prime, what I care is not about it has an upper bound. I want to go below, even below them too. So the upper bound is not an important thing. You can ignore it. So this is so far just about a few remarks about minor things. So any questions so far? Yeah, so if you don't have question, I will move to give you some idea of what how to do this. So well, since my startup base will be just dealing with cosine linear wave equation, so I begin with writing down a wave equation, and the kind of convention is the following. So if this is the equation for v, and then you read out this term on the right hand side. If this is an equation for rho, and you read out this term in the brackets for the right hand side. So this is my way of uniformizing the equation. So assume the vorticity is 0. We won't have the red parts, they are all 0. So this is general cosine linear wave equation. And in that situation, what are we going to do? So we start with assuming this total derivative of partial phi has satisfied this norm, is bounded by 1. This t is certain small number short lifespan to be chosen. We start with assuming this. Then we run energy estimates by just run through this energy estimate for wave equation. And then with the help of both, we try to establish Strichartz estimate, then derive this bound. So we hope to have the right-hand side is a constant multiple. This is what the less than similar means. Constant multiple of the t to the delta, and this delta is certain positive number. So then, as long as you can choose, you choose t sufficiently small, and then the whole bunch of terms will be less than 1, and then you close the argument. So you start with assuming something, and then you pay it back. So this is the kind of the strategy of doing the whole thing. Is this okay? Okay, so next page, I will further say how do I do this. So for achieving this, I will use Littlewood-Paley decomposition. So if you're not familiar with it, you think about it's a partition of unity, but not in physical space. So so we apply certain multiplier in the Fourier space, and this is induced by certain bound function supported in a dielectric shell, rescaling nicely, sum up to 1, and piecewisely they have like you can manage, and they kind of are localized in dielectric shell. In the Fourier space. Then we we work on this high frequency piece. This lambda is certain dielectric number. We focus on the large lambda, and so for lambda smaller than this number, we just apply a standard Bernstein inequality. If you don't like the name, you think about a certain Sobolev type of inequality. So in any case, we focus on large lambda, and if we can achieve this on the right hand side, and then sum over all these large lambdas, we are able to get the estimate in the previous page, and this number is the delta over there. And if you are curious, this lambda to certain power actually comes from my s is greater than 2. So you can kind of squeeze tiny bit of this delta, minus delta, from your s minus 1, from your s minus 2. So this is really coming from that. Anyway, so this is sort of what I want to have. But of course, I'm not going to tell you how, give you the detail of how to derive 11. So what I'm going to do is try to say something about how this works for Euler. So next page, I'm going to say, I'm going to adapt what I've said to Euler equation. So from now on, the phi here is going to be V or rho. Okay, so I probably changed the letter. I just look at linear wave equation, and this portrays this one, and the right hand side would be your F. So it's a kind of rough, direct way of treating this problem. So suppose we are going to just treat it directly, and you may wonder, what is the assumption that we need for the vorticity? So that's kind of this is the main problem I should work on, right? So let's see. Okay, so now I'm going to run this direct treatment. We consider the linear wave equation, and we start with, like, we assume we kind of start with the bootstrap assumption. And then with the help of this, we can run energy arguments, have the standard energy estimate for linear wave equation 12. And so the right hand side is just, this is rather standard. And then you plug in the right hand side of the equation for Euler equation, the box G V, box G rho, and you can find that the right hand side becomes this. So as I said, if it was back to cosine linear wave, this is something that I'm more familiar with, and sort of you don't need to worry too much about that. And this is the new term that I should worry, and we should have a story for this. Okay, so here this omega is vorticity, and this requires, well, because vorticity, you have nice transport equation along t direction. So this sort of means that it's it doesn't involve, like heuristically, it doesn't involve too much. So if you want it to be at T prime staying in this space, you better have it initially in this space. So it's natural to assume, I mean, you can do even better. So if you use this regime, you have to assume omega initially is in HS. However, my assumption in the theorem is HS prime. S prime is strictly less than S. So this is the first place I feel I'm over my budget. I cannot go further. This is the first place, and there will be more. So and also then, I mean, keep this in mind. And the other question is that if initially your omega is in this space, can it stay in this space? So so do we really have curl omega T prime is bounded in this space? This is the straightforward question. So to answer this, it brings you another difficulty. So let's see. If we use transport equation to give the estimate about curve omega, so the C is just a normalized version of curve omega. So if we just to do this HS -1 energy estimate for it, and we notice that the right hand side, this is quite standard product estimate. So if we look at this term, it's V at HS level, up to HS level. So it's almost like the highest possible space that you could put partial V in. So therefore, you can only put partial omega in L infinity. And this is just okay, but this term forces you to put partial omega in this norm. And again, because omega doesn't change that much heuristically, so you better put it initially in L infinity. But due to ellipticity, so you put a little bit more here. So this forces you to assume initially the space derivative of omega is in C00 plus. So hold the space. In terms of Sobolev embedding, this is H phi half plus for omega, and that is half derivative more than my assumption. So this is a bit too much. If you run this kind of direct treatment, just by these 2 pages, you feel, okay, you're definitely way over the budget. You can see this kind of regime in this paper, and they also include this dynamic, the case with dynamical entropy. I'm not going to elaborate, and I'm going to talk about something what I care more. So the failure of the energy estimate actually influence a lot more things. It's not just a bit is eclipse everything. So for instance, as I said, the kind of main regime is Strichartz estimate. So in Minkowski, the Strichartz estimate takes the following. So I use a very rough way to write it. If the solution, I mean, if we are considering box psi is equal to F in 3 plus 1, the Strichartz estimate looks like this. And again, so you need to put F in this space, and this F roughly are curve omega and Q partial phi, and they, again, you're back into the previous trouble and having no control on this. So this is the naive case in Minkowski. So that says even if I have this estimate and this Q is slightly greater than 2, but you won't be able to have a strict low loss LT2 estimate. Anyway, so you can only have this. You probably have you already lose the control on this term. You won't control this term. And so this gets you fail to control, for instance, partial G. And this psi is written as G because psi was V and C, was V and rho. Essentially, they are metric component. So anyway, so if you lose this and lose energy, and you lose Strichartz estimates in the curved background. But remember, we are in a rough curved space-time. If you want to implement all the known analysis in Minkowski, there should be some limitation, some requirements about the background metric. And you, in the naive case, you can't recover the noise control. You can't get the noise control about the metric. And it happens that they are the kind of minimal assumption about having a nice Strichartz estimate in the curved background. So it also collapses your Strichartz estimate in the curved background. So basically, yeah, it's just if without either a nice assumption on the initial vorticity or a nice way of doing it, you can't really do anything. So but actually I assure you this can be done. You don't have to worry about this. In the next page, I tell you what is my reason to adding half derivative on top of my original conjecture. So this phase, this seems to be a bit jump from the previous page, but it's still about Strichartz estimate. So when I do this, I think energy estimate is something can be solved directly. So I will tell you how later. But there is one thing that's my main concern. So this is the regularity about non-hypersurface. This is crucially related to establishing Strichartz estimate itself. So if you're not familiar with Strichartz estimate itself, we look at box psi equals 0, the naive one, and we run TT star duality arguments, and it also relies on full representation of the solution, and you also need to analyze the decay of the kernel and then apply the Hardy-Littlewood-Sobolev. So this is the kind of standard way. But in the curved background, so the first question is that how do you represent your solution? So there are many ways. So different author offers a different way. So you can see in the work of Smith, Shimon, Buhari, Shimon, and Tataru. What's done differently in Kleinemann's work is he used instead the kind of parametrics or like pseudo solution. He actually used the actual solution of the linear wave equation. So, and then he, by several steps of reduction, he kind of reduced the decay estimates to bounding the Moravec's energy. So in either way, no matter it's more like parametrics construction or this kind of bounding Moravec's energy, these two methods all rely on non-hypersurface. In the parametrics, the optical function is directly in the parametrics construction, and and also Moravec's energy itself is by definition is actually just rely on the null tetrad, which is defined by null hypersurfaces. So they're all tied crucially to null hypersurfaces. In a rough spacetime, null hypersurface is quite rough. So there was strategy of smoothing the background metric and truncate the frequency, all the sorts of things actually wasn't, I mean, it didn't work for AX0. So it's like you can't really manage it to work to the S greater than 2 case. If S greater than 2 plus something else, that's fine, but not S greater than 2. So in the sharp case, we all, like Smith, Tataru, and my works, all are on we work on linearized equation in the actual spacetime. So the actual spacetime is still rough, and because the derivative allowed for the metric is pretty limited. So if you're not sure what the definition of non-hypersurface is, so this is the level set of optical function, and optical function is defined by using the iconal equation. So if you're geometrically, I kind of use level sets of light combs, in particular the outgoing ones, to foliate the domain of dependence. So U in Minkowski is T minus R, and the light cone in Minkowski is really just this. And also, what kind of quantity, you wonder, do I need for to control the light cone? So, sorry? Can you, I mean, do you have any questions? Sorry.
Probably not, I guess. I mean, it's, yeah.
Okay, sorry. Yeah.
Noise, yeah.
Okay, so yeah, I hope it's like I didn't get you lost. So the essential thing is the main quantity is really GR. So this is the Richard-Hur equation, and we need to control at least null expansion. This quantity, I write it in. You have a geometric way of defining it. I write it in box GU, normalized by certain null ups, and so it satisfies a nice transport equation. Nice because the right hand side is Ricci, the component of Ricci, and L is in Minkowski is partial T plus partial R, and so yeah, it's like this. And well, of course, this L should be in the curved spacetime is the generalized version of that. So so this is a Ricci evaluated by L, and there are also a lot of low order terms. So at this point, I could explain why Einstein equation is a nice equation, because for Einstein, this is 0, right? So this is really a nice equation if you are working for the equation of Einstein. But cosine linear wave is not, for cosine linear wave, RLL is still a second derivative of metric, so or the solution. So it doesn't really cancel any derivative. So this makes the difference between Einstein vacuum and the cosine linear wave. And for Euler equation, it has one more term, which is related to the vorticity derivative. So I will, so of course for cosine linear wave, there are different levels of like requirements on treating RLL. So I will move to the next page explaining to you about how to deal with this Ricci component. So in local coordinates, you kind of, you express, you can decompose a Ricci curvature into this. And the leading term is box GG. And in Einstein, this psi is 0. But it's not, because now it's not Einstein, it's more than general cosine linear wave. It has, I mean, it's just a, I mean, so it's just there, some derivative of G. And this is some nice term, quadratic and partial G. So if I evaluate it by L, and it's this two falls on here. And also when I substitute box G rho, box GV, I have a term like this. And all other terms goes to this. So this is the structure of RLL. So in general cosine linear wave, when this is a way, I already seen difficulty if I want to do just achieve S greater than 2 by using commuting vector field approach. On top of Einstein, I have to do something more. So at the time I use geometric normalization. So I do conformal change the metric. The light cone doesn't change, but the geometric quantity that I have to deal with changed a little bit, but crucially. So then I use some other way, like uncanonical way to bound Morris energy. This is due to Duffmus and Wojniewski. I use this way to gain a bit more control, just good enough for controlling the additional term that the difficult term, so that I could patch them together and to get it done. So this is for S greater than 2 general cosine linear wave. But Euler equation, of course, you need that. But on top of that, you have one more term. So Euler or general cosine linear wave is just differed by one more term. but it's kind of hard. It's very hard term if you don't give it enough assumptions regularity initially. So if initially you assume, for instance, C00 plus, and you won't have any difficulty in treating this term. You have enough regularity for just propagating it. So this is one convenience if you assume more, but if you don't, you have trouble. So I won't kind of spend more time at this point on this kind of treating RLL. I try to close my story for energy estimate, give you a kind of a clear view of what, at least for energy estimate, what I did. So just now I said, if you want to use a direct way to consider the problem, you need additional assumption like A and B. And the thing is that I don't have them, but I can comfortably close my energy estimates. But Strichartz estimate posed me another difficulty. But anyway, so what can I do? What did I do? So to answer this question, I start with decompose velocity. So it's like Strichartz estimate is really for something that disperse, but compressible Euler equation, the solution doesn't necessarily disperse like a wave. So I have to break it into two parts. One part is something like determined by vorticity, so it's sort of transported. One part is I call it wave function. So this part disperse better. So for this part, I hope to establish nice Strichartz estimate. For this part, I do elliptic estimate. So this is the strategy. So then, of course, if I want to do Strichartz estimate for this one, I derive wave equation. So this is the wave equation I derived for this wave function part of V. So it turns out that the right-hand side is not as nice as expected. So it has still a high order linear term, which is like, where you started from. So it doesn't look good for now, up to now, but I can keep it and saying all other terms are fine. And I realized that I have a way of dealing with this term. So the way of dealing with it is first to try a different method of linearized original equation. So instead of writing it just straightforwardly in this way, I write it in this way. So which is exactly what's going on here. So write it in a fancier way. And all this are actually fine, just the leading term is important. So if this is the equation of V plus, then Y is T eta. If this is the equation of rho, then Y is 0. And then, so you sort of start to think about cancellation for doing energy estimate. You can introduce a certain modified current. Sorry, I kind of almost run out of my time. So I still have a bit of time. Am I right? So let me try to close that.
Like 5 minutes, like 10 minutes.
Yeah, I think that's good enough for closing. So so if you run, standard, energy current to do, use the standard energy current to do energy estimate, you have only this term. And if you add certain terms here, and then you will see in the whole calculation, there's no Ty in your calculation at all. So this is how this magic comes, just adding terms to cancel Ty. So this is actually, I did it for, in my previous work for Einstein for a different reason, but it works very, very well in this situation. And also technically there are other parts that can save me, time to estimate Ty. So, but this is for energy. For Strichartz estimate, is there, I'm going to do Strichartz estimate for just a standard box G psi equals 0. And all this kind of ugly right-hand side can be written into some initial data term according to according to Duhamel principle. So you won't be bothered by them. You won't need to estimate Ty at all. So this is again can be seen in my previous work. So then the energy estimate and reduction argument for Strichartz estimate can be closed at the level of the conjecture level. So you can get the HS minus 1 energy for partial V partial rho by just needing this much derivative on omega. And this is exactly, if you count carefully, this is omega H3 half plus. So that's exactly the conjecture level. So this is why I think the conjecture is reasonable. And but unfortunately, Strichartz estimate itself, in particular, controlling trace chi, that part need a bit more, need half derivative more. So I need this to bound this norm for any time, for initially at least, and then you can run it, you can control it at any time t in the lifespan. So well, next page I will just try to use maybe 2 minutes to close the whole thing. So just previously I said, if you go for a rough treatment to controlling curve omega, you will have trouble. You will require L infinity norm of partial omega. But if you do it in a more delicate way, so now, for instance, my C here is curve omega. So if you try to control double curve omega in L2, what you do? You just run your standard argument and then write carefully this term. So using an evolution equation, the right-hand side is this. So now calculate this carefully. You will see terms like this, a lot of terms, ... So looking at this term, if you want to have, for instance, just to bound them, I know that V in principle should be in H2 plus. This is already two derivative on V. So this seems to be now L2, L infinity, and this you hope it to be in L2, and then one grown one. But this seems to be like requiring partial omega in L infinity. So this is quite bad if you do it like this. Similarly, this is L2 because rho is in H2 plus a little bit. So this L2, this force partial omega again in L infinity. So it seems to be that we are back in the same situation. However, if you carefully look at this again, so partial m falling on this term is 0, right? So by taking advantage of this structure, you run integration by part in level set of t, and then this save you one derivative. So this falls on this term is gone, and when it falls on this is just the right. So this is the first place that you can save one derivative. Similarly, for this term, if you look at this, we know that when t hit on curve C, double curve omega, you know that T omega save your one derivative. T double curve omega also save you one derivative. So then this just drive us to integrate by parts in space and time. So we draw out this T, put a big bracket, and then there are terms when, then this T hit on the remaining terms. So at this point you save derivative, and this goes to the boundary, and this is unimportant terms. So then again, a derivative is saved. So by observing all these structures, you can bound L2 norm of double curve. And this, if you want to go a little bit more, you can actually, this is a bit too technical. So you can do that. And for, by doing the, and also by running the same energy argument, you actually can obtain energy flux along null hypersurface. But the thing is that this curve is not the curve along the null cone. So due to this kind of inconsistency, if you want to restrict the energy on null cone from the energy estimate, you sort of lose half derivative by using the trace inequality. So this is what you have. And this is short of 1/2 derivative to bound this. So this is by kind of, if roughly you do this energy estimate, you will lose 1/2 derivative for controlling curve, double curve omega along null hypersurface. But there is a special structure in the there. So in the null hypersurface for the null structure equations. So I assure you, this is just right. And so that's why I add half more and don't add more. So you have a structure to rely on, and that's just get you there and complete the whole argument. So this is sort of the whole story. I think I am already running over my time. So let me, thank you.
Right, thank you for this amazing talk. Yes, now we'll take questions. So if anybody has any questions, please go ahead.
Yeah, thanks for the talk. Yeah, I really like the delicate geometric idea in your analysis.
Oh, thank you.
Yeah, so I have my first question is about the conformal change when you mention about the estimate of the curvature. So can you elaborate a little bit on this?
Yes, I actually have a page. This was that's actually the hardest part, but that was actually for general cosine linear wave equation. So I have this. I mean, let me find it in the. This is my previous thing. Yes. So let me. So it's a bit hard to jump it to here. So when I do this Morris energy estimate, I need to deal with deformation tensor of those vector field for deriving the Morris energy and multiplier. So at that time, so I sort of need to control this deformation tensors and the derivative of deformation tensors. So this was all in the original setup of null frames. So by choosing, if I like make a conformal change of the metric, the null hypersurface is still the same null hypersurface. And after the change, you can see because of the deformation, the definition of the conformal energy is slightly changed. Therefore, this quantity is slightly changed as well. For instance, this quantity is going to be something together with something, and this is going to be something together with something. So by nicely choosing this conformal factor, I can try to manage to, for instance, this quantity together with the other. This too actually could have a cancellation. So they themselves are hard to calculate, are hard to estimate, but they actually have a very delicate cancellation. I'm not quite sure if I still have that page. So this was the quantity that appeared later after the conformal change. And I mean, after calculation, we find, okay, so the transport equation for mu is not good. The right-hand side is nasty. And the transport equation for those terms are not, is also bad. And the right-hand side is impossible to estimate. But when you add them together, the right-hand side becomes a box. So that's nice because we have a cosine linear wave equation here, so it has a big cancellation. So this is the trick that as long as you choose your sigma nice, you can basically cancel the bad bit of mu. So that's the idea. But it's quite, this takes a lot of calculation, definitely. So this is sort of from the general cosine linear wave. This is a very nice question. Yes. Thank you.
Yeah, thank you. And may I ask one more question? Yeah, because in the Einstein equation, we know the gauge is pretty important, right? So different gauge will.
Yes, you're right. Yes.
So in the analysis of this compressible Euler equation, will the choice of gauge play some role?
I mean, I've never heard the gauge problem. You can't really choose gauge. For instance, let's see. So for Einstein equation, yeah, for instance, if you choose gauge, you can cancel this, right? So this term is 0 with your choice of gauge. Yeah. But Euler, this is just, you have a fixed, I mean, expression for this. You can actually have a, I mean, there is no cancellation. It's just a del, first the derivative of phi. You can't really choose.
So you mean there's no
room for doing. Yeah, no, there's no room for doing that. But the structure of the equation itself is not that bad, but it has something fixed there. The difficulty is not kind of like Einstein. You can choose a gauge to kind of to cancel it. It's not an Euler or cosine wave for both. You can't really do that. It's just a fixed there.
This is intrinsic difficulty.
Yeah, if you have some other things like, yeah, it could be, but somehow this is not.
Yeah. Thank you. Yeah, that's all my questions.
Yeah, thank you.
Do you have any more questions? Yeah, I guess that, I'll ask a couple of basic questions.
So, please, yeah.
Yeah, so so the Littlewood-Paley decomposition that you use, for the Strichartz estimate, those all of this Littlewood-Paley theory, is it? So this is on this acoustic metric, right? It's not on a fixed.
This Littlewood-Paley is still on the standard one, because you think about the metric, it's conformally flat.
Right.
This simplify a lot, really. So
right.
You can switch between, you most of the time use Euclidean, then attach your c to the -2 or c to the 2.
Right. Yeah, that makes sense. Okay. Yeah, and okay, and another question was can you use so you talked about some parametric. So since you have a kind of a quadrilinear wave equation for the velocity and the density, can you use some sort of parametrics like those Klein-Rodiansky parametrics, or
no, their parametrics is physical one. So I also have from my breakdown criterion, I use the
right. Yeah, exactly.
Also, I have a 2D one. No, that's not the same. So you probably, if you are interested, the kind of more geometric way of, so first of all, the one by Tataru-Smith, that one is, already can get you whatever you want. So, and also for the one that's used in the L2 curvature conjecture, there is also a parametrics. That's sort of mixture of geometry and also the Fourier. So, but they are kind of inspired by Tataru-Smith anyway. So if you prefer the geometric kind of one, you can look at that. But those are all, I feel that's more like Fourier. This can only be, it's not the physical one. The physical one actually doesn't save you derivative. It's not,
right.
It's not, the purpose is not saving your derivative. Right.
Yeah, so I guess the whole complication is because you have this extra sort of the vortex phenomena, like the vorticity thing, which is kind of messing everything up. Like if you did have only sound, just zero vorticity, you'd have much simpler life. Life would be much simpler, something like that.
Yeah.
This is okay. Yeah, so this is I guess correct me if I'm wrong. So I guess this is the one of the most important differences between the Einstein and the Euler, because Einstein you have only the wave. There is no this sort of vorticity or something, right? So you have null structure.
Almost. Einstein is even slightly better because the structure is Ricci.
Right, exactly.
It's too nice. Right. It's the nicest extreme of 0, right? So right. For Euler, you have on top of the first the derivative with the gauge part, right? You also have a vorticity part, right? So that's sort of the extreme, or the other extreme, right?
Right. Yeah,
But yeah, these are all kind of from the, if you try to compare Ricci curvature, you can see they have this kind of difference. But of course, I mean, if you think about other ways, although I don't know, but that could be, I don't know, other ways of doing it. But in terms of GR people, I think this is sort of the way we kind of are used to.
Right. Yeah. Totally. Yeah. All right. Very nice talk. Very nice talk. And let's thank Professor Yang, Professor Wang for one more time, I guess. Let's thank everybody. And I guess we'll see everybody next week for the GR seminar. I'll just pause the recording for now.